So in this video, we are going to be solving a problem on Rankine cycle. So this question says, steam is the working fluid in an ideal Rankine cycle. Saturated vapor enters the turbine at 8 megapascal and saturated liquid exits the condenser at 0.008 megapascal. The net power output of the cycle is 100 megawatts. Determine for the cycle I, the thermal efficiency, II, the back work ratio, III, the mass flow rate of the steam in kilograms per hour, IV, the rate of heat transfer into the working fluid as it passes through the boiler in megawatts, V, the rate of heat transfer from the condensing steam as it passes through the condenser in megawatts, VI, the mass flow rate of the condenser cooling water in kilograms per hour. If cooling water enters the condenser at 15 degrees Celsius and exits at 35 degrees Celsius. Okay, so let's pick out our parameters. So first we are given that saturated vapor enters the turbine at 8 megapascal. So our force pressure P1 equals 8 megapascal and saturated liquid exits the condenser at 0.008 megapascal. So P2 equals 0.008 megapascal. Now they said the net power output of the cycle is 100 megawatts. So power output P out equals 100 megawatts. So the first question is to find the cycle efficiency. Okay, so before we come back to these parameters, let's describe the whole thing in the TS diagram. So this is the TS diagram that represents the Rankine cycle. So from state 4 to state 1 is the heat addition process. From state 1 to state 2 is the work rejection from the turbine. From state 2 to state 3 is the condenser heat removal or heat removal from the condenser process. From state 3 to state 4 is the pump process where work is being done on the system. Okay, now the properties at state 1 is what we found here. P1 is given as 8 megapascal. Now keep in mind, 1 bar is equal to 10 to the power of 5 Pascal. Now we have 8 megapascal. Mega is 10 to the power of 6. So this simply implies that 10 bar will be equal to 1 megapascal. Okay, 10 bar is going to be equal to 1 megapascal. So we have P1 to be 8 megapascal. That means in bar is going to be 8 times 10 to give us in 1 megapascal. So it's going to be 80 bar, right? So P1 is going to be 80 bar. So if 10 bar is 1 megapascal, it simply means that 0.008 megapascal. So we simply multiply this by 10 to give us in pascal or to give us the value in bar, right? So if you multiply 0.008 by 10, you simply have 0.08 in bar. Okay, so P2 is actually 0.08 bar. 0.08 bar, and the second pressure operates here, P2 equals 0.08 bar. All right, now keeping this in mind, we have to now find the value of enthalpy at state 1, at state 2, state 3, and state 4. Now enthalpy at state 1 is simply H1, and this value is obtained. Now since there is no temperature given here, it means we are not going to be heading to the superheated steam table to find the value of enthalpy, right? Since there is no temperature, it means now that enthalpy at state 1 is going to be the Hg from saturated water and steam table corresponding to 80 bar. Any value we get for Hg becomes our H1. So we are going to be finding that shortly. Similarly, our S1 entropy at that state is also going to be what? Sg corresponding to this same pressure 80 bar. So now we move to saturated water and steam table corresponding to pressure 80 bar. What is the value of H1? H1 is Hg at that particular pressure and S1 is Sg at that particular pressure. So let's see what that value gives to us. Let's go to our steam table now.
So now we move to the saturated water and steam table corresponding to 80 bar. So this is the pressure line, and if you move down here, you're going to see the enthalpy. So what we are looking for is Hg and Sg. Hg is H1, that's the enthalpy at 80 bar, and Sg is S1, entropy at 80 bar. So those are the two terms we are looking for. So we trace down to 80 bar. We trace down to 80 bar. Okay, I think this is 80 bar. So we trace now to the enthalpy line. So for 80 bar, you can see the Hg here is H1 2758. So if you trace up, you can see corresponding Hg. So 2758 is our H1. Then S1 is Sg. S1 here is 5.744. So that's Sg, as can be seen here. Sg 5.744. Okay, so keep these values in mind.
So corresponding to 80 bar, H1 is 2758. 2758 in kilojoules per kilogram. So that's Hg at that pressure. Similarly, we find S1 corresponding to which is Sg, still at that same pressure. So Sg gave us 5.744 kilojoules per kilograms Kelvin. So we have S1. So these are the properties at state 1, and we pause. Now we move to state 2. Observe that state 2 is in between the mixed vapor, a combination of saturated liquid and vapor, right? So since it's in between the mixed vapor, it means we need to find what is called the dryness fraction, X2 at this state. We need to find dryness fraction S2. Now, to do this, we first of all understand that state 1 and state 2 is isentropic, which means that state 1 and state 2 is a constant entropy process. How do you prove this? If I draw a line simply from this point down, you see that state 1 and state 2 is touching the entropy line. This simply implies that S1 is equal to what? S2. State 1 is equal to state 2. The entropy at state 1 equals the entropy at state 2. So if you have this, we already know the value of our S1 known. So we need to find S2, the entropy at state 2. To get this, we simply employ the relationship. This is equal to SF at state 2 plus X2 SFG at state 2. Simple. So what we're looking for now is X2 being the dryness fraction. Now, why are we going to be looking for X2? That's simply because to find the enthalpy at state 2, which is H2, H2 itself is going to be equal to HF2 plus X2 HFG. So that's the relationship to find the enthalpy at state 2 because it is a mixed vapor, right? So we have the fluid and we have the gas. For that reason, we need to find the dryness at that point. So this helps us to find the dryness fraction. And once we have this, we can now plug into this equation to get the enthalpy at state 2. Remember, all the formulas in Rankine cycle are related by the enthalpy. So all we are doing right now is to find the enthalpy at state 1, enthalpy at state 2, enthalpy at state 3, and enthalpy at state 4. Then we'll apply all our formulas to get our results. Okay. Now, let's see. We know what S2 is. Sorry, we know what S1 is. We've gotten the value of S1 as 5.744. So now we recall from this equation, 5.744 is equal to, so we need to now find SF as state 2 and SFG as state 2. Now, how do we get this? SF as state 2 is the entropy at the fluid region, SF, corresponding to the second pressure, 0.08 bar. Similarly, SFG is the enthalpy at the mixed vapor, corresponding also what to this second pressure, 0.08 bar. So now we go to the saturated water and steam table, corresponding to 0.08 bar. We find SF at that point. We find SFG at that point. We can also find HF and HFG all together at once. So let's do that. At 0.08 bar, saturated water and steam table. So we find SF. This SF is now labeled as SF2 because we are at state 2. So let's go to the steam table corresponding to 0.08 bar.
So now move to pressure 0.08 bar. We need to find HF, HFG, SF, SFG. So SF becomes SF2, that's at state 2. SFG becomes SFG2 at state 2, then HF becomes HF2, HFG becomes HFG2 simply because we are state 2. So we trace 0.08 bar. This is 0.08 bar. So if you move, you're going to find the value of HF. This is 174. So let's pull it up a little bit. So this is HF is 174. HF is 174. Then HFG is 2402. So if you trace, this is HFG. So this is now HFG2 2402. Okay. Next we'll move to SF. SF is 0.593. So this SF is SF2. As can be seen here, SF 0.593. Okay, we'll move to SFG. SFG2 is 7.634. So if you trace, you find it SFG. Okay, so let's fall back to the calculation now.
So corresponding to 0.08 bar, SF is 0.593. So 0.593 kilojoules per kilograms Kelvin. Then SFG2, so we'll find SFG as well. That's 7.634. That gives us 7.634 kilojoules per kilograms Kelvin. So we have SF and SFG. Next, let's find HF, which is now HF2, still at that same pressure. So we find HF. HF is 174. So we have 174 kilojoules per kilograms. Then we'll find HFG at that same pressure. So HFG is 2402. We have 2402 kilojoules per kilograms. Now that we have these parameters, let's now plug back into this equation. So enthalpy at state 1 is equal to x2, which is equal to this. Now SF2, we have the value of SF2 here to be 0.593. So this is equal to 0.593 plus x2 multiplies SFG2. So our SFG2 gave us 7.624. Okay, so we'll have plus 7.624x2. So with this, we can now find the dryness fraction. So what do we do now? Let's put 0.593 over here. So we have 5.744 minus 0.593 to be equal to 7.624x2. So let's find this difference. 5.744 minus 0.593. That gives us 5.151. So we have 5.151 equals 7.624x2. So we make x2 subject. This implies x2 equals 5.151 divided 7.624. This implies that the dryness fraction at state 2 is going to be equal to divide 7.624. So that gives us approximately 0.68. So this means that the dryness fraction at that point is 0.68. So if we know the dryness fraction, we now plug into this equation. Okay, we now plug into this equation to find our second enthalpy, H2. So we can do that over here. So H2 is going to be equal to, remember the formula, it says HF2, and we have the value of HF2 here to be 174. Okay, so we have 174 plus, remember x2 multiplies HFG, but now we know what x2 is, 0.68. So plus 0.68 multiply XFG, sorry, HFG2, which gave us here to be 2402. So multiplies 2402. So H2 is going to be equal to, so I'll punch everything all together, 0.68 multiplies 2402 plus 174. So that gives us 180, 1807.36 kilojoules per kilogram. So we've been able to find the enthalpy at state 2. Now we know what H2 is. Next, we move to state 3. We need to find the enthalpy at state 3. But if you observe, state 3 is directly on the liquid line. This line is a liquid line. This line is the vapor line. State 3 is directly on the liquid line. Since it is directly on the liquid line, it means that dryness fraction at this point, x3 is equal to 0. And if it is equal to 0, if you relate that with this equation of enthalpy, considering now state 3, this becomes H3 equals HF3 plus X3 HFG3. But if X3 is 0, it means automatically everything here becomes 0. So H3 becomes what? HF3. So this simply means that enthalpy at state 3 will correspond to the fluid enthalpy of this pressure, 0.08 bar from the steam table. Okay, so therefore H3 is going to now be equal to what? HF at that state. Simple. Corresponding to at 0.08 bar from the steam table, from the saturated water and steam table. It's as simple as that because it is directly on the liquid line. So there is no dryness. Everything there is completely what? Purely liquid. So X3 is 0. So we simply move to the saturated water and steam table corresponding to 0.08 bar. What is now HF? That is what we found there as HF2, 174. So this becomes what? The enthalpy at state 3. So therefore, H3 equals 174 kilojoules per kilogram. So this is now our third enthalpy. This is our third enthalpy, H3. So we have the enthalpies at state 1, enthalpy at state 2, and enthalpy at state 3. Finally, we need to find the enthalpy at state 4. So if you observe that state 4 is quite strange, it is not on the liquid line, it is actually out of the liquid line. So this simply means that we are going to be employing a different equation because from state 3 to state 4 is a pump work region. This is where pump does work on the system from state 3 to state 4, compresses the fluid back, compresses the fluid back to state 4 before it is now added to state 1, right? So for that reason, we employ a special equation. To do this, we employ the pump equation. The pump work equation, WP is equal to volume at the fluid region multiplied by change in pressure. And that change in pressure becomes P1 minus P2. That's the difference in pressure. So if you have this, you cannot be able to find your H4 because pump work relates to the enthalpies at state 3 and state 4. Enthalpy at state 4 is H4, enthalpy at state 3 is H3, which we found here. Then pump work has another formula, WP equals, it becomes H3 minus H4 or H4 minus H3. I think the lowest minus the highest so that you can be able to achieve the negative pump. You understand? Negative pump because pump work is usually negative. So it becomes H4 minus H3. So with this, you can now make H4 subject to the formula and find what H4 is if you know the pump work. So this helps us to find the pump work and this helps us to find the enthalpy at state 4. So what we are going to be doing now is we know the two pressures involved. We need to find the volume of the fluid corresponding to that pressure. And the pressure we are looking at now is pressure between the compressor. Remember from state 3 to state 4 is the compressing region and the pressure that governs the state is still 0.08 bar. So now we consult our steam table corresponding to 0.08 bar. We need to find the volume of the fluid at that particular pressure from saturated water and steam table. So let's go to our steam table and see. So from the steam table, there is no exact 0.08, but what we have there is 0.0779, 0.0821, and we need 0.08. So we simply interpolate, right? We simply interpolate. So let's interpolate to get, these are the values of our pressure. The first pressure there is 0.0779. What we're looking for is 0.08. And what we have there next is 0.0821. So this will help us to find, by this interpolation, we can be able to find the pressure, the volume corresponding to 0.08. So what we're looking for is the volume of the fluid. So corresponding to 0.0779, the volume of the fluid is 0.001008. 0.001008. Meanwhile, corresponding to 0.08, we don't have it. So label that as VF. corresponding to 0.821, 0.0821, we have it to be 0.001009. 0.001009. So we simply interpolate from here. With that interpolation, we can be able to find the volume at the fluid corresponding to 0.08. So we need space now. Okay. Now we find, so we interpolate simply. This is the shortest way to interpolate. So we use last minus the first all over last minus the middle. We maintain the same thing on the right hand side. So last is 0.0821. So we have 0.0821 minus 0.0779 all over last 0.0821 minus the middle 0.08 equal to, maintain the same thing on the right hand side, last minus the first. So I have 0.001009 minus 0.001008 all over last minus the middle. So 0.001009 minus VF. So I have all over 0.001009 minus VF. And we have this. So let's compute. So I'll just punch everything here to save time. I'll punch everything at the numerator and at the denominator as well. All right, so after analysis, we'll have VF to be equal to 0.00100085. So from here, you can either cross multiply, this multiplies this, and this multiplies the whole of this, then find the value of VF, right? Or you can simply divide this by this, then cross multiply as well, find the value of VF. You have it to be this. Just in case you find any trouble with this, you can type on the comment section, or you can reach out to me via WhatsApp, and I'm going to respond to you how I got this. But simply cross multiply and you're going to find the value of VF. So I did this just to save time, right? Okay, so now we know the value of VF. We can now find the pump work. So pump work is now going to be equal to, we know what VF is, 0.001008 multiplied by change in pressure. So our pressure is 80 bar minus 0.08 bar. So 80 minus 0.08 bar. So let's see what this gives us. This implies that our pump work is now going to be equal to, so this gives us approximately 8.06 kilojoules per kilogram. So this is now our pump work. So if you know the pump work, you can now plug into this particular equation to find the enthalpy at state 4. Okay, so what do we not need? We don't need this. We also don't need this. All right, so you recall from here you can make H4 subject. This means H4 is going to be equal to pump work plus H3 if negative H3 crosses over. So our enthalpy at state 4 is now, our pump work, remember, is 8.06 plus H3. We have the value of H3, or we found it earlier here as 174. So plus 174. So we converted this to kilojoules per kilograms simply because the enthalpy is also expressed in kilojoules per kilogram. So what we did is simply multiply by 1000 to convert to kilojoules. Okay. So from here you can find H4 to be equal to 8.06 plus 174. So that gives us 182.06 kilojoules per kilogram. So we have now all the enthalpies. Everything we need is set. So we can now employ all our formulas to start solving. We have all our enthalpies. So let's start by the first question. The first question says we should find the cycle efficiency. So you know that efficiency is net work all over heat supplied. So we need to find the net work. We know what the pump work is. We need to find what the turbine work is. Turbine work is simply between state 1 and state 2. Work removal from the turbine. And that work is positive. So it is simply H1 minus H2. So turbine work equals H1 minus H2. And that's equal to our first enthalpy H1, we have the value here to be 2758. Okay, 2758. So we have 2758 minus H2. We have H2 here to be 1807.36. So you have 1807.36. Okay. So this implies that turbine work is equal to, let's see what we have, 2758 minus 1807.36. So that gave us 950.64. So our turbine work is 950.64 kilojoules per kilogram. So if we know the turbine work, then we can find the net work. So our net work is going to be turbine work minus pump work. Remember, pump work is always negative, so that's why you have to attach that minus there. That gives us our net work. So this is equal to, turbine work gave us 950.64, 950.64 minus our pump work. We found our pump work here, 8.06 minus 8.06. So net work is equal to, let's find that value, 950.64 minus 8.06. That gives us 942.58. 942.58 kilojoules per kilogram. So we have our network. Next, we find the heat supplied. Heat supplied is between state 4 and state 1. Okay, heat is supplied between state 4 and state 1. And that heat supplied is equal to enthalpy at state 1 minus H4 because it is positive. Heat added to a system is always positive. So now H1 minus H4. This is going to be equal to H1. Once again, H1 gave us here 2758. So you have 2758 minus H4. And we found our H4 earlier here to be 182.06. 182.06. So this means our heat supplied QS is equal to 2758 minus 182.06. So that gives us 2575.94. We have 2575.94 in kilojoules per kilogram. So now we have the heat supplied, we have the network, we can now find our cycle efficiency. Efficiency therefore equals network 942.58 942.58 divides by heat supplied 2575.94. Multiply this now by 100%. This implies that our cycle efficiency is going to be equal to, so let's find it. So that simply gives us approximately 37%. You can call that, or 36.6%, or you can approximate to what, 37%, whichever. But that's the cycle efficiency. So first question answered. The second question says we should find the back work ratio. Okay, so the back work ratio is simply the ratio of the negative work to the positive work. So back work ratio is negative work, which is the pump work, divided by the positive work, which is the turbine work. So that's the formula. The pump work divided by the turbine work. So the pump work, once again, we have the pump work to be equal to, okay, here, 8.06. So you have 8.06 divided by our turbine work, right? Turbine work gave us 950.64. Divide 950.64. You can as well multiply this by 100 if you wish. 100% since it's a ratio. So back work ratio. So it's actually a reversal work ratio, right? So it's the pump work divided by the turbine work. So the value is going to be equal to, let's point it and see. That gives us 0.0084. So you can multiply by 100%. Okay. If you do that, you have it to be 0.85 approximately. 0.85%. So that's our back work ratio, 0.85%. Okay, the next question says we should find the mass flow rate of steam. So to find the mass flow rate of steam, we use the relationship. We are given power output. Power output is equal to mass flow rate multiplied by the network. Okay, mass flow rate multiplied by the network. Now this power output can also be labeled as W dot, something as the power output. And we're given the value initially as 100. So the power output was given to us as 100 megawatts equals 100 megawatts. So from the equation, if you make mass flow rate subject of the formula, it becomes the power output all over the network. All over the network. So this is going to be equal to our power output was given to us as remember, power output was given in the equation as 100 megawatts. So it is important to know 1 megawatt is equal to 10 to the power of 6 watts or joules per second. 10 to the power of 6 joules per second. Joule per second is everything as watts, right? Joules per second. Now, if we convert this is also going to be 1 megawatt is also going to be equal to 10 to the power of 6 has 10 to the power of 3 multiplies 10 to the power of 3, right? So 10 to the power of 3, one of it becomes kilo. So this is now 10 to the power of 3 kilojoules per second. So we simply convert to kilojoules because the network is expressed in kilojoules per kilograms. Kilojoules, network here is expressed in kilojoules per kilograms. Okay, so for that reason, you convert this to from megawatt to kilojoules. So this becomes 10 to the power of 3 kilojoules per second. So our output power becomes 100 times 10 to the power of 3. This is now in kilojoules per seconds. Divided by our network. Network was given here. We found the value as 942.58. So you have 942.58 kilojoules per kilograms. So we can take this off now. So from here, mass flow rate is now going to be, so you observe here, kilojoules cancels kilojoules. We have now kilograms per second. Now this is how the units are. If we're dividing the unit, we have kilojoules per second. Okay, now divides by kilojoules per kilograms. So if we remove this division sign and introduce multiplication, it becomes kilojoules per second multiplies kilograms per kilojoules. So kilojoules cancels kilojoules. So which means at the final answer, what we have becomes kilograms per second, right? That's what we're going to have, kilograms per second. So our mass flow rate is now going to be, let's find this, 100 times 10 to the power of 3 divides 954.58, 942.58, sorry. So this means our mass flow rate is approximately 106, okay, 106.1 kilograms per second. Okay. But we were asked to find this value in kilograms per hour, right? So we simply, to find it in kilograms per hour, we multiply by 3,600 seconds. So this is going to be 106.1 multiplies 3,600 seconds. That converts it to kilograms per hour. So this means our mass flow rate is going to now be, so let's multiply this value by 3,600. So this implies our mass flow rate is going to be, so if you multiply these two together, you have 381,960 kilograms per hour. So this becomes our mass flow rate. Okay. So having found the mass flow rate, we'll move to the next question. Next question says the rate of heat transfer into the boiler. Okay, rate of heat transfer into the boiler. So we are simply to find the rate of heat transfer in the boiler. Boiler is between state 1, state 4 and state 1. This is the boiler where heat is added. Okay, so the rate of heat transfer in the boiler is between state 4 and state 1. Heat transfer rate Q dot is equal to mass flow rate multiply by the heat supplied by the boiler. Simply heat supplied multiplied by heat supplied. So we know what the mass flow rate is. We know what heat supplied is. Simple. Plug that into the equation. We get the heat rate. Okay. So the heat supplied rate in the boiler equals mass flow rate now. Please, we're not going to use this because this particular mass flow rate is expressed in kilogram per hour. We need this particular mass flow rate which is expressed in kilogram per seconds because this will give us the true unit of work heat flow rate. Heat flow rate is something as power, and power is kilojoules per second and not kilojoules per hour. Okay, so for that reason, we'll make use of this 106.1 multiplied by heat supplied. Heat supplied gave us 2575.94. So multiplies 2575.94. So if you observe, let's include the units. Let's include the unit and see. So the unit for the mass flow rate is kilograms per second multiplies unit of the heat supplied is kilojoules per kilogram. So you observe that kilograms cancels kilograms, so I'm left with kilojoules per second, which gives us the true unit of power, okay, which is the heat flow rate. So heat flow rate is now going to be equal to, let's find this multiple, 106.1 multiplied by 2575.94. So that gives us 273307.234, and this is going to be in kilojoules per second, okay, and that's approximately kilowatts because joules per second is watts, so you have kilo there, that's kilowatts. So this is actually equivalent to heat flow rate equals either 273,307.234 kilowatts, or you can convert this to megawatts, pull it 3 backwards. Heat flow rate is now going to be equal to 273 point. That's, if you move the decimal place now, 123, or multiply simply by 10 to the power of -3. So that converts it to mega, 273.307 megawatts. Okay, megawatts. So you can either choose to leave it in megawatts or, okay, no, the question says we should keep it in megawatts. So this is the value in megawatts and not in kilowatts. So that's the answer we are looking for. Okay, we'll move to the next question. Next question says heat rejected in the condenser. So heat rejected in the condenser. Condenser is between state 2 and state 3. And heat rejection becomes now H2 minus H3. Now it should be negative, right? So you can simply say H3 minus H2 because condenser, once heat is removed from the system, it becomes negative. So it can be H3 minus H2. Negative sign there shows heat rejection. Okay. So the heat rejected in the condenser, okay, heat rejected, call that QR, becomes H3 minus H2. Okay, so heat rejection should be negative. So it becomes H3 minus H2. And we know the value of H3. H3 gave us here, okay, here 174. So heat rejected equals 174 minus H2. H2, sorry, H3. Yeah, H3 is 174. And H2 is 1807.36. 1807.36. So heat rejected equals 174 minus 1807.36. So that gives us negative 1633, 1633.36. So this is in kilojoules per kilogram. So the negative sign actually shows heat rejection. But the question says we should find this in megawatts, right? So which means we need to multiply this by what? The mass flow rates. We need to multiply this by the mass flow rate to get it in megawatts. So the heat rate rejected, the heat rate rejected becomes mass flow rate multiplied by what? The heat rejected. And that's equal to mass flow rate gave us 106 multiplies. So you can choose to neglect the negative sign now, or you can still decide to work with it. It doesn't really matter, but the negative sign just simply shows heat rejection, right? So multiply by 1633.36. Okay, so our heat rate, rejection rate is going to be equal to, so we are multiplying this value by 106.1. So this gives us, like I said, you can choose to include negative sign if you wish. So if you include the negative sign, you're going to have negative 17, 32.99.496. So this is now in kilowatts. This is now in kilowatts. So to convert to megawatts, this implies the heat rate or heat rejection rate is going to be equal to, so simply divide by 1000. So or pull this three step backwards, you have negative 173 point approximately 30 in megawatts. So that becomes our heat rejection rate in megawatts. And finally, the last question says the cooling water mass flow rate. Cooling water mass flow rate, when you're given temperatures between 15 degrees Celsius and 35 degrees Celsius. Okay. So cooling water mass flow rate, given we have T1 to be 35 degrees Celsius and T2 to be 15 degrees Celsius. The equation we are going to use is simply the equation for specific heat capacity. So cooling water heat rate is equal to mass flow rate multiplied by Cp multiplied by change in temperature. So our change in temperature becomes 35 minus 25, right? Minus 15, please. Minus 15. So this is going to be equal to 20 degrees Celsius or Kelvin. Anyone can work at this point, okay? Now, our Cp for air is 4.18 kilojoules per kilograms Kelvin. So we need to find m dot, which is the cooling water mass flow rate. And the cooling water is water coming out from the condenser. So which means the heat rate is the heat rejection rate that we're going to be using, because heat rejection is at the condenser. So this heat rate becomes our heat rejection rate, which we found here to be this 173.30 megawatts. Okay. Okay. So if we make m dot subject on the formula, we're now going to have this to be heat rejection rate divided by Cp times change in temperature. So this is going to be equal to, our heat rejection rate is this. So we are not going to work now with negative sign. Keep it and work with the absolute value. So you have 173299, 173299.496. So this is in kilowatts. Okay. Divided by Cp. Cp is 4.18 multiplied by change in temperature, will give us 20. Okay, so this implies that our mass flow rate for the heat rejection is going to be equal to, so that gives us 2072.96, 2072.96. This is now in kilograms per seconds. So, but they asked us to find this in kilograms per hour. We simply multiply that value by 3600. So let's do that over here. The mass flow rate of cooling water is now going to be equal to, so we're multiplying this value by 3600 seconds. So that gives us 7462657.72 kilograms per hour. All right, so that's the last and final question for that given Rankine cycle problem. Please, just in case you have any issues with the calculation at any point at all, you can draw my attention via the comment section, or you can hit me up via WhatsApp displayed on my screen. I will see you in the next video with another question. Thanks.